Hello, everyone. I'm Yifan. Currently, I'm a postdoc with Professor Daniel Kuhn. And today, I'll be talking about uniform convergence for stochastic minimax optimization problems. So what is stochastic minimax optimization problems? It is a model like this. We want to minimize over x while maximizing over y. So it is widely seen in generative adversarial networks, and it's also widely used in zero-sum games. But in practice, normally we do not have access to the true distribution of this randomness. Instead, we normally have access to a data set S that consists of n samples, IID samples. So in this paper, we are going to consider the nonconvex regime. Basically, this small f function is going to be nonconvex in x, but strongly concave or concave in y. When we solve this type of problems, because we can only solve the right-hand side empirical optimization problem, let's say we have some algorithm that gives us some output on x, and we denote it as AS. Then an interesting question that we want to ask is how the solution given by this algorithm, because it's coming from the empirical problem, how does this solution generalizes on the populational problem? And in particular, we want to characterize such generalization bounds measured by stationality. Basically, the stationality means that we are taking the gradient with respect to this phi function. Before coming into our approach, we want to briefly highlight what are the drawbacks of existing stability-based generalization bounds. By stability-based generalization bounds, we really mean that there's a lot of papers that studies generalization, and in particular, they will first analyze the so-called stability of an algorithm, which means if you have a data set, you use algorithm to output some points, and then if you perturb one sample within this data set, you will get another point. And stability basically means how far away these two outputs are. Once they have the stability, they get the generalization. However, we want to highlight that immediately you will see this type of stability-based generalization bounds requires to analyze each algorithm, SGD, proximal gradient type of, and it's very hard to analyze those stability for complicated algorithms, for example, the widely used AdaGrad or ADAM. Secondly, there's a mismatch in terms of step sizes. To achieve small generalization, they require step sizes that does not give you small optimization error. Thirdly, this type of analysis, because of its nature, it only holds for function value optimality gap. So in the nonconvex regime, it really didn't tell us much about how you are, because we are only converging to a stationary point. And fourthly, this type of generalization bounds actually grows to infinity as your algorithm runs, which is not true. So to overcome all these issues, we propose to utilize this so-called uniform convergence and propose this algorithm-agnostic generalization bounds. The idea is extremely simple. The left-hand side is just a generalization error of an algorithm, while the right-hand side, we replace the output of the algorithm by the maximum over any point within the domain. So naturally, this right-hand side provides an upper bound, and if we can bound the right-hand side, basically we restrict that the empirical function has to approximate the population function. Of course, to upper bound the right-hand side, we need several techniques. For example, covering number, concentration inequalities. Also, we need so-called stability of empirical risk minimization on this y for a given x. And in the paper, we devise a novel lemma how to link this nonconvex strongly concave problem to nonconvex concave problem while doing a regularization on y part. Once we get the upper bound on the right-hand side, this right-hand side provides an algorithm-agnostic generalization bound, so it works for any algorithm with any step sizes, so that would be nice. This is the main sample complexity result we get. So comparing to the stability-based generalization bounds, we have additional dependence on the dimension. But we would like to highlight that this is the first uniform convergence results. So it addresses all the, you don't need to do case-by-case analysis. You don't need to worry about mismatched step sizes. And in particular, we handle these stationary points, so it also works for nonconvex optimization problems. And the second interesting observation is that actually, for this type of generalization bounds, there actually exists an upper bound on the generalization that depends only on the structure of your problem, not the algorithm. So let's looking back on the fourth drawbacks of the so-called stability-based generalization. Let me give you a figure here. This blue line basically denotes the generalization bounds derived by stability analysis. You will see that as the number of iterations goes, this algorithm runs longer and longer, the generalization, it says that the theory says that the generalization gets worse and worse. But we show that actually there's a red line that is totally vertical, and you shouldn't go above that. So in the future, we hope that to derive some kind of generalization bounds that looks like the black dash line, so that you will enjoy the benefits of stability-based generalization bounds also with a uniform upper bound. Thank you so much.